So for this video, we are going to address the VSEPR theory and how it ties into expanded octets. So what that means is that we have not just a coordination number of 4 around the central atom, we have 5 now, and we're going to do 6. So 5 electron domains around the central atom, or 6. So these are called expanded octets. And remember, the VSEPR theory, we really deal with the idea that we're maximizing distance between the atoms. Between the electrons, which is the bonds, right? Because these bonds are made of electrons. So one thing to note about the the 5 coordination number, right? So 5 electron domains, is that we have 2 that are 180 degrees apart from each other. And then I'm going to do this. See that? We have basically a trigonal planar within this, right? Don't we? So it's 120 degrees apart. So we have a couple degrees here that we could talk about. Technically, this is 180, this is 90, and these are 120. So this is a structure called Trigonal Bi-Pyramidal. And how they get that is, I'm going to cover this up. If I were to connect all these lines here, wouldn't I get a pyramid with a triangular base? Flip it, and I have the same thing over here. So bipyramidal because there's 2. So this is the electron geometry. So the electron geometry is always going to be called trigonal bi-pyramidal. Okay. So if we have 6 bonds, we have, what angles were we talking about? We had 90, we had 120, and technically we have 180, don't we? All right. So if we were to remove 1 electron, let's figure out where that 1 electron would come from. The electron, now we're going to also identify, this is the only one you really have to pay attention with this, is there's something called the axial and the equatorial. Axial electrons the axial electron domains are the ones that are 180 apart from each other, so it's sort of an axis, and then these are equatorial. I got a marker on myself. So axial and equatorial. So are we removing an axial or an equatorial? So let's look at what would happen if I took an electron from here. Or took the atom from here, and now this is the lone pair. Is this maximizing repulsion like the VSEPR theory would like? Remember, lone pairs get their way a little bit more than the other ones do. So this is 90 degrees away from three bonds. That's pretty close. How about if I took it from here? Now it's 90 degrees away from 2. Ooh, and 120 degrees away from the other ones. So this is the position where we would like to take our electron from. So this is the position that would maximize distance between the electrons, the lone pair and the electrons involved in the bond. So this is, if we had 5 bonds, 1 lone pair. What are the bond angles involved in this? We still have our 180, we still have our 90, and we still have the 120 between those. So it's all the same ones, right? All the same ones from that. So what do we call this, though? What is this shape? So what's the electron geometry? What we said earlier? Electron geometry is always going to be trigonal bipyramidal, because the electrons are in that shape, aren't they? But what about the molecule itself? So you could always, when you're looking at molecular geometry, you could take away the lone pairs. This is my favorite one. It's called seesaw. Why do they call it that? Because we actually made a little seesaw. See? So that's fun. So we made a little seesaw. That is the name of the molecular geometry. Right? have 5 bonds and 1 lone pair. I'm sorry, 4 bonds and 1 lone pair. Am I just not counting right? Oh yeah, you guys are probably screaming at home. 5 bonds, and then this is 4 bonds and 1 lone pair. This would be 3 bonds. I'm so sorry, guys. And 2 lone pair, right? So where do we take the electrons from? Actually, these are as far apart as possible as they can be, right? So what they do is they take from the equatorial, like we did for the seesaw, molecular geometry, and then we also take 1 more. So what shape is that? And what bond angles do I have? So if I were to want to look at the molecular shape, we can now remove the electrons. Remember, the electron geometry is always still going to be trigonal bi-pyramidal. But what's the shape? It is a T shape. So what are my bond angles here? I no longer have the 2 equatorial bonds coming out here, so I no longer have 120. I just have 90 and 180. So for 3 bonds and 2 lone pairs, it's called a T-shaped. T-shaped. And we just have 90 degrees and 180 for this one. And then which one would I clearly lose if I were to lose 1 more? Would I lose this one? No, because then these bonds are very close to each other. I need to maximize. So if you have 2 bonds and 3 lone pairs, you have linear. And what bond angle do we have here? 180. I can spell too, I swear. Okay. Linear 180. All right. So let's go down the rabbit hole with the other shape. Sorry, with the expanded octet of 6. I'm putting back my my molecules together here on the side. All right, so let's look at what it would look like if we had 6 electron domains. Bam. So, even though we have 6 electron domains, this is called an let me double check with the verbiage. This is called an what is the verbiage? I just need to double check. This is called an octahedral. Yes. Now, it may seem a little misleading. So octahedral is the electron geometry, e.g. Octahedrals are electron geometry for that situation. So, if we have all 6 bonds, so that is misleading, isn't it? Because we have 6 electron domains, but we put the word oct in there. Now, if any of you ever played Dungeons and Dragons and stuff, this is if we were to connect everything, like make this a side, make this a side, this a side, this a side, and this, like, you know, make it a 3D model. This would have 8 sides, so that's why it's an octagon. So if we had 6 bonds, so they were all bonds, what bond angles are we seeing here? I'm seeing 90, and I'm seeing technically 180, right? So if on your exam or something you just said 90, I would count it correct. But you could also say there's 180s there, just to be, you know, thorough. So, since all of these are technically equal, there's really no axial or equatorial, because this is the same as this. So, the only axial equatorial that really matters is in this situation. for an octagon, for an octahedral, if we remove one, what bond angles do I have for the molecule? I still just have 90 and 180, right? 180 from here to here, and 90, 90. So if we had, oh, I don't know why I keep putting that lid on. Having a rough time. If we had 5 bonds and 1 lone pair, we still have 90 and 180. What do we think the name is going to be now? So if I remove this, that's technically called a square pyramid. So it's a square pyramidal. Because if we were to connect the lines here and here, it would be a square pyramid. So this is square pyramidal. What if we were to lose another? So remember, this is the molecular geometry. What's the electron geometry? It's always going to be octahedral. So let's remove one more. So what if we had 4 bonds and 2 lone pair? Well, that 2 right there, 2 lone pair. Would we remove this one and have our lone pairs be right next to each other? No, we want to use the VSEPR theory and maximize the distance. So we're going to go 180 degrees away from it. What's this shape? This is called square planar because it's in one plane and it forms a square. What are my bond angles here? Still 90 and 180. But this is called a square planar. I'm going to abbreviate a little bit here. Square planar. What if we were to remove another one? Yet another one. That is where, actually I just looked and we don't have any more where we go any further into this. There's just those 3 different molecular geometries that we're going to be using for the octahedral electron geometry set. So let's look at one problem from your homework. It's number 30. What is the molecular geometry of a compound that has 3 bonds and 2 non-bonding? So if it has 3 bonds and 2 non-bonding, that has an electron domain of 5, total of 5. So we're talking about AB5. This guy right here, right? So it's saying that we have 2 bonded and 3 bonded and 2 non-bonded. So 3 bonded, 2 non-bonded. So that is where we remove the equatorial and you move another equatorial. So the molecular shape is the connectivity, the actual bonds. That's a T-shaped. When you type it in, make sure that you use a dash, T-dash shaped. And again, just to refresh you, what's my electron pair geometry? Still Trigonal Bi-Pyramidal. But what's my molecular geometry? That's going to be T-shaped. Alright guys, I hope this helped out.